math is easier.
It'll make the blackboard a little bit more bearable.
That means I'm now back to an A.
Are you talking about overall or on that test?
Just on this test. You said, I thought we had we were like, if you fill out the...
But if I don't want to discuss your grade in front of everyone, but
No, it's not great.
so if you add 20, like, let's see, an A on this test is 150 points, right? So,
Yeah.
and the A starts at 135.
Okay, so I have a B on this test, but I have an 89 point something in this class right now. So I'm sure if you bump this up even 2 points, it would jump me back to a 90 flat.
Anyway, this much is true. Adding 20 points helps, but hopefully not really, because you're going to replace this test with the final exam. So let's talk about the solution to the problems. As this one was, so I have the solution posted already, right? So, but the solution to problem 1 is wrong because I forgot a 2. And so there's 2 ways to do this problem. Now, some of you tried to do it a wrong way, which was to use the Pythagorean theorem. The Pythagorean identity only applies to right triangles. This is not a right triangle. It looked right enough. Well, anyway, so that's not right triangle. Can't use it. So if we use the law of cosines, so I'll show you 2 solutions, all right? First of all, law of cosine solution. So law of cosines says that c squared equals to a squared plus b squared minus 2ab cosine of the angle between a and b. So in my wrong solution, I neglected the 2. And that's why my solution as posted currently is wrong, but I fixed it and I'm going to post it again. So let's put this into practice here. 15 squared is equal to, let's see here, let's say a is 12. And so b is x squared minus 2 times 12 times x cosine of the angle between a and b, which is 40 degrees. All right, so this you can rewrite as x squared minus 24 times the cosine of 40 degrees x minus 81. And that is a quadratic equation. So we can use the quadratic formula if you like. X is 24 cosine of 40 plus or minus the square root of 24 cosine of 40 squared plus 4 times 81, because the minus and minus cancels, all divided by 2. And when you work that out, that will give you either 22.06 or minus 3.67. Obviously, this is the solution that you're looking for, because the other one can't be a length, right? So that's how we can do problem 1. Now, problem 1 was also, was this on test 2? I think this was one of the last problems in test 2, which I tried to warn you guys about. If it's not the last problem in test 2, it's something very much like it.
We might have gone over this in class.
Ah. Now, so that's the one way to do it. The other way to do it would be a law of sines approach, which is the approach you took, Jared. So law of sines says what? Like the sine of the angle over the length of the side is equal for all the different angles and sides, right? So let's see here. So we have sine of 40 over 15 equals the sine of A over x, right? Equals the sine, the last problem on what?
It was number 20 on, it was the last problem on test 2.
Last problem on test 2. Yeah, annoyingly, I am without ability to access computer today because it won't turn on. Unfortunately. Let's give a name to this other one. Let's call it, oh, it's B, right? So sine of B over what? 12, right? So this is the law of sines. And we can figure out what b is because we can solve, see this, if we look at this equal to that, we get sine of b is equal to 12 times the sine of 40 degrees divided by 15. So b is inverse sine of that quotient, right? And when you put that in your calculator, use degrees, what you get from that is 30.95 degrees, roughly speaking. All right? So how does that help? Well, that helps because we also know that the sum of the angles in the triangle is 180 degrees, right? So now I can figure out what b is from this. Excuse me, not b, a, right? So a is 180 degrees minus 30.95 degrees minus what? Minus 40 degrees, right? It has to be whatever's left from 180. That has to be what a is. So you calculate that subtraction, you get 109, or what do you get? 109.1, roughly speaking. And once you know that, you're in the clear, see, because you can go back to law of sines and solve for x, right? X is equal to sine of a over the sine of 40 times what? Times 15, right? So that's the sine of 109 divided by the sine of 40 degrees times 15. And that worked out to about 22.05. So as you can see, there's some numerical, right. Oh, you can round it up to 7. Okay, 6. Yeah. But so when you're dealing with a triangle which is not a right triangle, the tools of the trade are, law of cosines or law of sines. This is how we can relate angles and sides on a non-right triangle. The other way to do it, of course, is if you have points, if you have coordinates for the points, you can use the vectors that lie along the angles, and you can use the dot product, the angle relation to figure out angles. That's the intent of the later problem in this test. Problem 2, there was a lot of kind of, I would say, floundering, for lack of a better term. But if this is v and this is u, then I think some of you had the minus 2u, and that was good. The big problem for me grading was you didn't really have stuff labeled, so it was hard for me to figure out what your answer was. So I don't, I'm not sure what the right fix to that is in terms of test format, but it was a problem for me trying to figure out what your answer was for a lot of you. But let's see here. And then the other one, u plus v is basically, so this is u plus v, so like this. Let me erase that just to emphasize what the answer is here. This would be u plus v. I think my minus 2u is too long, but you guys get the idea. So you guys were not confident about how this works. You need to review these problems more, all right? It's not hard. You guys can get this one for sure, but I do think you need to review those a little bit more. Problem 3, you guys are just lost for the most part. Like, you're not really aware of the fact that e to the I theta is cosine theta plus I sine theta, right? And I'm not convinced that you guys know what Cartesian form means. What does Cartesian form mean? It means you put it in the form a plus ib, right? This is the fundamental thing we talked about in the complex section. So if I have 5 e to the I pi over 3, and I want to put it in the Cartesian form, I just use this relation. Like that. And, well, these are just special angle, right? So we know these. Cosine of pi over 3 is a half. Sine of pi over 3 is root 3 over 2. So we get, 5 halves plus I, 5 root 3 over 2. which for the purpose of graphing, it's nice to notice that that's about 2.5 plus 4.33i. Right, so as I'm plotting that, I go, okay, so like 2.5 over and 4.33 up, so that's basically where z1 is, right? So you could either plot it as a point, or you could draw the line to it. I don't mind. It's hard to see points sometimes, so the line is nice. It's helpful. So that was that. This is the Cartesian form right here, and that's the plot. Okay? What else did I say? Part B, I told you the magnitude of Z2 is 4, and the angle of Z2 is 210, right? Magnitude of Z2 is 4. The angle of Z2 is 210 degrees. So in order to use the Euler formula here, this is Euler formula. We need to do what? We need to convert to radians. How do you convert 210 degrees to radians? It's what? What's that? Pi over 180, right? So 180 is 6 times 30. 210 is 7 times 30, so that's 7/6 pi, I believe. And so Z2 is 4 times e to the 7 pi I over 6, which is 4 times cosine 7 pi over 6 plus I times the sine of 7 pi over 6, okay? So the main thing you guys have not absorbed is this is how we get from angles to the Cartesian form, right? Cosine plus I sine. You need to understand that's the bridge between the polar form, right? So notice that 5e to the I pi over 3, this is the polar form of Z1, all right? 4e to the 7 pi I over 6, this is the polar form of Z2. In this problem, I'm giving you the polar form and asking you to find the corresponding Cartesian form. That's what the problem is. And what does this work out to? It's, I think, minus, I forget. So that's minus the square root of 3 over 2 and minus 1/2. So minus I over 2. So that is equal to minus 2 root 3 minus 2i. And the decimal is about minus 3.46 and minus 2i. So I find decimals are helpful when I'm graphing, because you have it in a grid, so it's about here-ish, right? Which makes sense, right? Because this is 210 degrees, right? Whereas that is 60 degrees, also known as pi over 3. So part of the final exam is questions about conversion degrees to radians and finding the area of a sector, right? Now, as you go back and look at that stuff, it should be much, much easier now in retrospect, right? Most of you guys did pretty well on test 1 anyway, because I think I made test 1 with about 5% of my mental capacity. But so my test 1 is not a good test. My apologies for that. You're like, no, don't apologize. Please get sick again. No, wait, but you guys didn't say that. I wouldn't put that on you. But anyway, so there's problem 3. Okay. So the key thing I'm trying to get across here is that we have z. We can write it as x plus iy, or we can write it as r e to the I theta. This is the Cartesian form. Of z, right? This over here is the polar form. of z. And the polar form and the Cartesian form each have their place. What's the relation? E to the I theta is cosine theta plus I sine theta, right? And so that means x is our cosine theta, y is our sine theta when you match things up. So it's all tied back together with the whole polar coordinates business, which is why it's called the polar form. You're like, I know this. Yes. If you know these things, happy are ye if you do them on my test.
For y, would you do r I sine?
Nope, nope. Y is a real number. The I is, it sits there. Now, for problem 4, I spent some time in class trying to break down for a vector in 2 dimensions, right? If we have a vector and it's like this, right? We can write it as A1, A2, right? We can also write it as the magnitude times the unit vector, right? And if the angle is theta, how does it break down? Remember, it breaks down, this piece right here is a cosine theta. This length right here is a sine theta, right? The magnitude of this. So what I'm telling you is there's formulas. This is A2, this is A1. In other words, the vector, any vector, non-zero vector, can be written as magnitude cosine of the standard angle, magnitude sine of the standard angle. These are things we talked about in class. They should have been on your formula sheet. You should have been ready to use them. But that did not happen, at least as far as I could cipher. It's hard for me to judge. Some of you are writing vectors without writing the vector brackets. So like you have strings of numbers with like commas, but there's no vectors. Like I can't parse what you're writing. So it's possible some of you had like a right answer, more of a right answer than I realized, and I just couldn't see it because you didn't write the vectors. If that's the case, tell me. You know, I do make mistakes grading. I'm totally willing to look at it again. But again, I think that's kind of a moot point because I think you guys are going to do better on the final, right? So A in this problem, we're on problem 4, right? So part A, I told you that A was equal to 5 and that the angle for A was 45 degrees, right? Standard angle. And I told you that B had magnitude 5, right? And the angle for B is 180 degrees, right? So first of all, before I even do any calculations, in your mind's eye, what you're talking about is this, right? Here's A, 45 degrees, right? Here's B, 180 degrees. You really shouldn't need formulas to write down the explicit form of B, right? Once you draw that picture, you should immediately go, oh, B is minus 5, 0. We don't need formulas. We just need geometric understanding of what 180 degrees standard angle means, right? It's on the negative axis. But of course, the A is 5 cosine 45 degrees, 5 sine 45 degrees, right? Which is 1 over root 2. Well, it's 5 over root 2, 5 over root 2, right? I wish that silly projector worked today. Oh well. It's probably good for me to write it out. That's about 3.536, 3.536. Sorry if you can't see my scribblings. That's not approximate. That's equal. That's just straight up equals. So that was so there you go. That's the Cartesian form of A and the Cartesian form of B, right? I basically started you with a somewhat polar description of the vectors, you could say, right? I don't say that's a polar description of the vectors, but I would point out it's very much the same as the polar description of the complex number. It's standard angle, it's length, right? It's really the same math in a different notation if you get right down to it. And then part B was to algebraically calculate A plus B. So my wife took one look at this problem and she's like, well, if they can't do the first one, they can't do the second one. I'm like, yeah, that's just true. So, right, if you can't find those, you can't find A plus B. But if you can find those, A plus B is breeze, isn't it? You just add you know. So what is that? Minus 1.464. Come on, chalk. So there it is. There's a plus b, right? And what else? What's the magnitude of a plus b? I think if you had gotten this far, you could have answered that question, right? Most of you understand how to calculate the length of the vector, right? I have a hard time seeing it, but I think it's because you're confused about other parts of problems, like the fact that you know how to calculate the magnitude doesn't shine through because all I see is the confusion about the other part, you know, but I do think that you guys actually know that. So if you had come to a clear and confident understanding, that's a plus b, you probably could have done this, right? Just dump the minus signs, right? The minus sign gets eaten up in the squaring. So whatever that works out to, 3.83-ish. And how about the standard angle? So what quadrant is this in? I mean, I can calculate inverse tangent of the y component over this, right? Over the x component. And that will give me an angle, right, of minus 67.51 degrees. But that's not the standard angle of this vector, is it? Because if we picture a plus b, I could do it, a plus b is where? It's got a negative x and a positive y, right? It's over here somewhere, you know? So the angle puts us in quadrant 2, which means inverse tangent of y over x component doesn't do it for you, right? You have to add 180 to that. So since we're in quadrant 2, the angle is 112.49 degrees. So I was trying to walk you through the steps here of how to calculate. Another way of asking problem 4 is just to give you the information. A has magnitude 5, has angle 45 degrees. B has magnitude 5, has angle 180 degrees, right? And then the question would end with part C. Find the magnitude and standard angle of A plus B. Like, that is a way I might ask this question on the final. But you should understand, if you're asked such a question, the way to do it in parts is to, first of all, break down A into its Cartesian components. Then you break down, then once you've broken A and B into their Cartesian components, right, break down the vectors, then adding them is just algebra. And then we're back to the standard problem of find the magnitude and standard angle of a vector. So I was trying to be, you know, helpful to you. And then part D, the plotting, I'll add it to here. I'll put D right here. So that's A, and then B is like this, right? So A plus B, as I've indicated, is like over here somewhere. This is the tip to tail vector addition picture of this problem. Problem 5. Unless there's a question. So now I'm turning the tables. I'm giving you the Cartesian form, and I'm asking you to find the polar form, right? So like A, I got Z is minus 2 minus 2i, all right? I never turned the camera back. Oh, man. That was bad. Well, most of you are here. Yeah, sorry about that, internet people. Let's see here. Maybe there are no such people. I don't know. All right, so here we go. So how do you find the magnitude? Well, actually, even before I draw the magnitude, I think it's helpful, to calculate the magnitude. It's helpful just to picture the number. It's got -2 and -2, right? It's down here. And what's this angle? Because it's going the same over down as it's going left. That's a 45-degree angle, right? Because this is a 2 and a 2. And of course, this is 180, right? So the angle of Z is, 225 degrees. Or if you like to look at it another way, it's pi plus pi over 4 radians. So it's 5 pi over 4 radians. We need radians for the e to the I theta formula, right? And what's the magnitude? Square root of -2 squared plus -2 squared. I don't even bother writing the minuses half the time, but that's 4 plus 4, which is 8, square root of 8. And so therefore, Z is square root of 8, e to the I 5 pi over 4. There you go. That is the polar form of the complex number. Now, if you had told me that the standard angle is 5 pi over 4, or even 210 degrees, and also that the magnitude was square root of 8, and you hadn't written this, but you said that that pair of information was the polar form, I probably wouldn't have taken off points, all right? But as a matter of default, I am looking for this as the polar form. I think it's the healthy thing to think of as the polar form, truth be told. Now, B is easier. Z is equal to 3i in this case. So here's a picture. It's here. Right? What's the standard angle? 90 degrees, right? Which is pi over 2 radians. So this is 3 e to the I pi over 2. If you can rewrite the number as a positive number times an imaginary exponential, whatever's in front of the imaginary exponential has to be the length. Like if I tell you W is 83 e to the 13 pi I over 1,375, all right? The magnitude of W is 83. See, because the magnitude of any e to the I theta is the magnitude of cosine theta plus I sine theta, which is what? Square root, cosine squared plus sine squared, also known as square root of 1, also known as 1. And so when you take the magnitude of any complex number, if you have it written as number times imaginary exponential, that number, whatever it is, out front has to be the magnitude. Provided one thing, provided it is a positive number. If it's negative, you got work to do. All right, like if I wanted to, as an example, if I was given, say, W equals to -3 e to the I pi over 4, and I was asked to put that in polar form, that is actually something to do. See, I have to take that -1 and somehow get rid of it, So the way I would do that is, well, -1 is e to the I pi. So these are some shortcuts which are worth knowing. Like this one is based on the shortcut I is e to the pi I over 2, right? And that's true because cosine of pi over 2 is 0 and sine of pi over 2 is 1. So when you go to this, the Euler formula, which I have now erased, this is true because right, cosine of pi is -1, sine of pi is 0, so that's why e to the I pi is -1. So I could rewrite this as 3 e to the I pi over 4, which gives me 3 e to the 5 pi I over 4. There you go. This is the polar form of that complex number, which makes a lot of sense if you think about it, right? Because 3 e to the I pi over 4 is like here, right? And if you multiply by minus 1, you're down here. So multiplication by minus 1 is a rotation of 180 degrees, which is multiplication by e to the I pi. These are different ways of looking at it. Anyway, I'm digressing. Let me get back to your test. Problem 6. So now that I have gotten past the part of the test where I'm just trying to ascertain whether or not you guys were ready to convert from polar to Cartesian and vice versa, now we're actually putting it into practice. So like this one, you've got z is 3 plus I, w is minus 1 plus I, and I said find Cartesian and polar forms of z plus w to the 10th, right? All right, so first of all, what's z plus w? Well, that's easy. We just add, right? So we get 2 plus 2i, which, by the way, is square root of 8 e to the pi I over 4. See, you can picture z plus w is here, right? This is 2, this is 2, so that makes this angle 45 degrees, or pi over 4 radians, right? Did I? Oh, you did? Thank you. I'm so bad. Now, why do you want to go to polar? You want to go to polar because if you're going to raise something to the 10th power, if you have a Cartesian form, that means you got to like take a binomial and raise it to the 10th power. That's a lot of terms. Like you got to do a Pascal's triangle, like 10th line. It's like it's a pain. You don't want to do that. Polar form, on the other hand, is easy to take the 10th power of. So, and this is something we explored in examples in class and so forth. Right? So we've got square root of 8 to the 10th power, which is something horrible, but it's manageable. And e to the pi I over 4 to the 10th power, right? So the square root of 8 to the 10th power is actually 32,768. All right? And that gives you e to the 10 pi I over 4, which we know what to do. I won't try to be clever here. I'll just tell you that's cosine of 10 pi over 4 plus I times the sine of 10 pi over 4. Which is I, actually, because the cosine of 10 pi over 4 is 0, and the sine of 10 pi over 4 is 1. So we got 32,768 I. So there you go. That is the Cartesian form of the answer. 0 plus that if you want to be fussy. What's the polar form? Well, I need to convert I to an imaginary exponential. We already know that's the usual trick, e to the I pi over 2. So this is 32,768 e to the pi I over 2. There's the polar form of the answer. And if you start thinking through it, it makes a lot of sense, right? Because when you take this number and multiply it by itself, what happens? You're multiplying by e to the pi I over 4, right? So every multiplication by z plus w rotates 45 degrees. Do it 10 times. So you got like 1, 2, 3, 4, 5, 6, 7, 8 to get the first time around. And then the 9th one gets you to here. And so there's 9 multiplications in z to the 10th. That's why we got I. But you don't have to understand the geometry that I just rattled off to solve this problem, right? I was surprised that I don't think anybody got this problem, which was disconcerting to me. I'm glad I didn't ask more of them. So, problem 7. These are easy though. I mean, honestly. So you got x squared plus 2x plus y squared equal to 0. I said find the polar form of that. So to find the polar form of something, did you already? There's you 3 main tools, all right? And the 3 tools are this: x is equal to r cosine theta, y is equal to r sine theta, and you know another one that's nice to know is x squared plus y squared is what? It's r squared, because cosine squared plus sine squared is 1. So like, you know. And so as I look at this problem, I'm like, well, this x squared and this y squared gives me an r squared, and then plus 2x, which is 2r cosine theta. There you go. That, my friends, is the polar form of the equation. You could stop there if you wanted. If you wanted to further analyze this, it's interesting to do that. This is r times r plus 2 cosine theta equal to 0, right? Which either gives you what? R equals to 0, or r is equal to minus 2 cosine theta. And r equals to minus 2 cosine theta is something you could try graphing if you wanted. So it starts out at minus 2, gets back to minus 2, it's at 2 in the middle, it's something like that. So we're starting out at 0 at minus 2. So this is 0, but we got a minus, so that puts it over here. And then what? We get radius 0 at pi over 2. Let's see here. So we're kind of trying to think through this. We're going from here to here, so it's basically going like this to there, and then from pi over 2 to pi over 2 to pi, we're going from radius starting at 0 at pi over 2, and then back to like that. And then past pi, we're just going from pi. We're basically just, past this point, it just repeats itself, actually, if you keep going. This is a circle, right? Now, pre-calculus, how would we have seen that? We would have completed the square. See, this is x plus 1 squared plus y squared equals to 1. So it's a circle at minus 1, 0, center, right? Radius 1, right? Which is what I've just graphed using polar methods. This is 2, 1. Anyway, that's easier. Now the problem 8 was a messier problem. I'll let you look at the solution online. I'm not going to try to do it on the fly here. I think it's better for me to go on. The time is limited. You guys, you knew what you were supposed to get, kind of, sort of. You were in the hunt, a lot of you there. I should have made it odd. That would have made it easier, right? If I had made it like 3 theta, they would just have 3 petals. But where was I? So find the standard angle and degrees problem. So this, you know, side C was -3, -4, right? So that means the magnitude is the square root of 9 plus 16, which is square root of 25, which is 5. Great. And inverse tangent of -4 over -3 is 53.13 degrees. That is not the angle here, right? Because where is C? C is over here somewhere, right? So we need to go like that. That's going to be 180 degrees plus that 53.13 degrees. So the standard angle here was 233.13 degrees. If you don't understand how to calculate standard angle of a vector yet, that is the first thing you must fix. That it absolutely will be on the final, like that is certain. So nail that to the wall, right? Don't let me get you on that again. Here, vector D is 0, -10. So I picture it. It's like that, right? -10 down, right? So the magnitude is 10. A lot of you got that. Great. And the standard angle is 270 degrees, or I would also take -90 degrees. And so you got to be aware. This is where inverse tangent breaks down altogether. It's not a add 180 degrees. It's just not even defined. Inverse tangent of infinity. I mean, okay, if you extended the definition of inverse tangent, that inverse tangent of infinity was 90 degrees, and inverse tangent of minus infinity was -90 degrees, then you could make it work. But your calculator does not do that, as that is not standard mathematics. That is what you might call engineering mathematics. So problem 10. So you had A was 1, 2 minus 2. B was 304. So for A, the magnitude of A was 3. The magnitude of B was 5, because that's what you get from square root of 1 squared plus 2 squared plus 2 squared, yeah? That's the square root of 9, which is 3. And then the second one is the square root of 3 squared plus 0 squared plus 4 squared, which is square root of 25, yeah.
What are the 2 bars you put on mine? You put 2 bars A.
So this is that, which is not equal to this. These are scalars. This is vector. And only in one dimension can those be the same. So like numbers, vector. So we, when I drop the vector, it's the magnitude. That's the standard physics notation. What was A dot B here? A dot B was -5. That's 1 times 3 plus 2 times 0 plus -2 times 4, which is 3 minus 8, which is -5. And then to find the angle between these, right, we have a formula. Theta is inverse cosine of A dot B over the product of A and B, the magnitudes of A and B, which in this case works out to 109.47 degrees. And so are these vectors parallel? Are they perpendicular? Are they neither? Neither, right? It's not 90 degrees. It's not 0 degrees. So that's that. Problem 11 was A cross B. Yeah. And yeah, so you guys are wrong. Sorry. I'd like to sugarcoat it somehow otherwise, but you have yet to quite get your calculate the cross product formula down pat. And some of you were confident enough that you should have checked your answer, but you did not. Problem 11. So I'll just tell you the answer, A cross B, is in fact 4 minus 1, 1, right? So, yeah. And then problem 12. So I gave you, 3 points and find the triangle. I'll let you look at the solution of that. Let me just end with problem 13 here today. Problem 13, I had z was 625 exponential of 2 pi I over 3. That was given, right? And you're supposed to calculate the fourth root of z. So the way to do that is you calculate the fourth root of the magnitude, which in this case is 625, and then you take the exponential of 2 pi I over 3, and you have to divide by 4. So the fourth root of 625 is 5, and that's e to the pi I. 2 over 12 is 6, so e to the pi I over 6. So there you go. That is the fourth root of z. That's all you had to do. There it is. The fourth roots of z are basically the fourth root of z, and then I times the fourth root of z, I squared times the fourth root of z, I cubed times the fourth root of z. We did an example like this in class. All right. And to picture them, again, I'll post a solution here, but basically the fourth root is here, and the next one's here, the next one's here, the next one's here. If I could, oh, I haven't done it justice. So it's like I times it. These are the fourth roots. They're all in the, not in the unit circle, but the circle of radius 5. So, and then problem 14, again, I'll let you look at the solution. You guys are not quite where you need to be on those problems yet. Listen, I think for the sake of, I think, it's not entirely standard material in here. So as a show of good faith to you guys, or to accommodate whatever you want to say, pick your favorite phrase here. I'm not going to put three-dimensional vectors on the final. I think 2 dimensions is enough for us in here. I can still ask the triangle question in a 2-dimensional sense, right? I don't need to make it have a 3 dimensions, but so I will do that for you guys. That'll simplify things a bit.
You said what triangle?
Like problem 12 is stated as a 3-dimensional problem, but I could easily convert that to a 2-dimensional problem. So I'm not trying to rule that out necessarily. I might actually give you that problem where I have the points graphed on a grid. So you could, that would allow you other ways to solve that problem. Yeah, the final is comprehensive, that is true. I wanted to give you guys the course survey today, but the stupid printer would not work. It's got some toner thing full, I don't even know. The electronic one, yes, but I give one, but I hand one out to you guys, and then one of you will take it to the secretary, and then I see them after the semester. That way because I'm going to have a problem in here, like explaining like my teaching and stuff, because all the classes have most of my classes have less than 5 students, so I'm only getting course evaluations from intermediate algebra, which I don't think is really an adequate representation of my teaching. I hope I'm doing a good job in there, but I do teach other things, So, and generally my students in other classes are somewhat less grumpy. I'd be grumpy too if I was